Hello, I'm Anna Mackay and today we're graphing cubic functions. So in the textbook there are some investigations that are worth looking into to explore these functions. Here's a summary of them. So the graph of a cubic in this general form has this shape when a is greater than 0. So the way I think of it is that you're increasing first if a is greater than 0, and if a was less than 0, you decrease first. As the size of A increases, we get steeper, and the graph in this form can be obtained by looking at the standard, if you like, cubic function, and then it's some translations, a horizontal and a vertical translation. Interesting, it can be thought of in terms of a vector, and we're actually going to look at vectors in the other maths later in the year. Just one example to start with, if we get asked to graph on the same set of axes, the general cubic, x cubed, and this one. So let's have a think about what we would have. I'm going to draw it like this. So our general cubic of y equals x cubed goes through the origin there, and it's got this flattening out type of thing. It's not a cut like a linear factor. And because a is 1, so we're greater than 0, we are increasing first. So we're going to come from the bottom here and then going up. And label that y equals x cubed. Now our second one, you might think of it as a horizontal shift. Now remember the signs change, so it's a shift to the right of 2 and it's moved down 1. So think about the origin there. If you had to shift that point to the right 2, here we go, jump, jump, and down 1, perhaps put a dot there, for that's where that flattening section is going to happen. And then you might think about other points being shifted across 2, down 1. Maybe a point down here, across 2, down 1. I sometimes find it helpful to put little dots and then connect the dots for when you're doing a sketch. Gives you a rough idea of where you're going through. So then I like to try and visualise out the graph that I'm going to draw before I draw it, like that, and then off I go. And there we are, labelling that to finish. And here it is drawn neatly, like that. Okay, some other facts from these cubic functions. That if a is greater than 0, not only does it increase to start with, there's two shapes that it could have, depending on if it's got linear factors or a cubic factor there. Now, this is interesting. Each cubic polynomial must cut the x-axis at least once. And so it has at least one real 0. If you investigate polynomials more, you'll see that the odd power there means that they will all have this fact. So things with an odd power, 3, 5, even 1, in unique cases, they'll have to cut the axis at least once. And the other ones would be a touch, the repeated roots there, or they might not be real. So let's look at these. So you could have 3 linear factors, and that would look like this. You could have 1 linear factor, and each linear factor implies a cut, so hence that beta here. And the repeated root at alpha is a touch there. And then the other forms are if it's a cubic repeated root, if you like. So it does cut through the axis, but it has also got a flattening out section that's unique to the cubics that happens there at that triple root. And then the last form perhaps is where you could have 1 linear factor and a quadratic factor, if you like, but there are no real roots in here. And so the one real factor cuts through, and then the other one has what would look like a touch had it been a real factors, but it's the flattening out higher up. All right, on to some questions. Use the axis intercepts to sketch the graph of these cubics. So, axis intercepts. So let's start, first of all, by thinking about the x-intercepts. What are they? -3, 1, and 3. And our y-intercept, we therefore know that x is equal to 0, so you substitute that in for y. And that gives us 18. So there are axis intercepts, and thinking about that a value, what number is that? 2, so it's greater than 1, so we're going to increase to start with. So graphing that, we would put on our x-intercepts to start with, thinking about what scale you might use. So putting 1 at -3, 1 at 1, and 1 at +3. And that y-intercept is at 18 up here. This is just a rough sketch. Now, which way do you start with for your cubic? Do you come up into 3 or down? Because a is greater than 1, we're going to increase first. And think about how do we get through that 18? Somewhere up here before we come down and cut through and then cut through again. So let's connect the dots. Bit of a rough sketch there. My scale's not very good to allow for that 18, but you get the idea. And ideally labelling the graph for that one. Okay. Oh, and there's it drawn neatly. Okay, second one. X-intercepts to start with. X-intercepts are, we've got +2 here and -1/2. And what's significant about the x-intercept at 2? It's going to be a touch. Could be worth writing that underneath to remind you when you come to draw it. Y-intercept, what value does x have? 0. Substitute that in. And solving, we get -4. So when we come to graph this, think about your scale. Here are our x numbers and our y. So putting on some values here, I might have a half almost as my scale, and down to -4. What's that a value? It's negative, so we're going to descend first. Now, there's a touch at 2, so I sometimes like to put that factor there. Now it's going to come from underneath because we are starting from above with the half. So there's the cut happening down here and a touch at 2, and now connect the dots. We don't know where that minimum is, that turning point. We just know it has to cut through at -4. And here it is drawn neatly. There we go. What about reversed? What if we get given the graph and we have to work out the equation? So think back to what we needed last time round to find. We had to find the x-intercepts and find the y-intercept. So this time around, those x-intercepts will be handy. I advise writing them out. So x-intercepts are what? -1, 2 and 4, and therefore as factors they are that with the opposite sign. Notice that I've put the a out the front there, and that's what we need to solve for now. So we need a point to sub in. So we've used -1, 2 and 4. What other points are left? This point here, but sub it in as a coordinate, and its x value at that point would be 0. So substituting that in, so where we see an x, we're putting a 0, and where we're seeing y, we're putting -8. So we are left with solving for a. We get a is equal to -1, and rewriting the final equation with that a value. As you know, we don't have to put the 1 there, we can just put the negative, and there's our final equation. Great. Last one, find the equation of the cubic with this graph. Now, what factors can you see here? We've got an x-intercept here and here, but what's significant about them? This one is a cut, so it's a linear factor, and the second one here is a touch, so that's a repeated factor. So let's identify them first. Our x-intercepts are -3 and +2 on 3, and that is a touch. So when we come to write the general form, the first one we would have x plus 3, and this second one, the rearranging of that fraction, 3x opposite sign, take 2 and squared because it's a touch. Now we need to solve for a, so we substitute in an unused point, so that's 6 there. I'm going to sub in 0, 6, and I'll write that out. Solving for a, we have a is equal to 1/2. So I'm going to substitute that back in, and I'm just going to rewrite it in a slightly different order. I'm going to put the repeated factor first. We tend to put the highest powers of x first, and that repeated factor here would create an x squared, so that's why we tend to put that factor first. Okay, that's the end of this polynomial series. Thank you for joining me. See you next time. Subscribe and tell your friends. Thank you.